Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We reached this point in this last class. We found that the deform length is given by this quantity here. What is that quantity? Let me remind you. If we have a point at alpha 1 comma alpha 2 comma alpha 3 and another point a differential distance away, alpha 1 plus d alpha 1, alpha 2 plus d alpha 2, alpha 3 plus d alpha 3, then this original distance, original undeformed distance, we said it is ds whole squared, or the square of the distance. Okay. Now when it deforms, this point moves to alpha 1 plus xi 1, alpha 2 plus xi 2, alpha 3 plus xi 3, and this point moves to alpha 1 plus d alpha 1 plus the rigid body movement plus the elongation, comma alpha 2 plus d alpha 2 plus xi 2 plus d xi 2, and this is alpha 3 plus d alpha 3 plus xi 3 plus d xi 3, and this distance is ds dash squared. That's what we have over here. Okay. So our Gij looks like, okay, let me ds dash whole squared in a compact form can be written as I j Gij d alpha I d alpha j, where Gij can be given as G I plus sigma over k del G I by del alpha k xi k delta ij plus G I del xi I by del alpha j plus G j del xi j del alpha I. Okay. So you can see that Gij is equal to Gji. Okay. So now let's see. If we have 2 points, so examples. If we have 2 points, okay, example, let's say one point is at alpha 1, alpha 2, alpha 3, the other point is at alpha 1 plus d alpha 1, alpha 2 plus d alpha 2 and alpha 3. So there is only this differential which is non-zero. Then what is my ds square? If you remember, it was g11 d alpha 1 squared plus g22 d alpha 2 squared plus g33 d alpha 3 squared. So in this case, d alpha 2 is 0, d alpha 3 is 0, and so this is equal to g11 d alpha 1 square, the undeformed length squared. Okay, and so ds dash whole squared now will be g11 d alpha 1 squared from here. Okay, from here. Similarly, if second example, very similar, if we have a point at alpha 1, alpha 2, alpha 3, and the second point is at alpha 1, alpha 2 plus d alpha 2, alpha 3, then the undeformed squared length is g22 d alpha 2 squared, and the deformed length is g22 d alpha 2 squared. Now, a slightly different case, case number 3. Okay, so we have a point. So let me just give an example for this, or a picture for this. Alpha 1, alpha 2, alpha 3. Okay, so the first point is at alpha 1, alpha 2, alpha 3, and the other point is here. Okay, at alpha 1, alpha 2 plus d alpha 2, alpha 3. The next example is this is alpha 1, this is alpha 2, alpha 3. So we have a point now at alpha 1 plus d alpha alpha 1, alpha 2 plus d alpha 2, alpha 3, and a point here which is alpha 1 plus d alpha 1, alpha 2, alpha 3. Okay, so what is the distance between these 2 points? What is the distance between these 2 points, or what is the distance between these 2 points? And then what is the deformed distance? Okay, so now if we look at this formula here, we look at this formula for undeformed distance. So ds square is simple, is equal to g11 d alpha 1 squared plus g22 d alpha 2 squared. Okay, but in order to find the ds dash whole squared, okay, we have to have one point at alpha 1, alpha 2, alpha 3. Okay. So what is that? I will move this point by minus d alpha 1, and I will move this point by minus d alpha 1. Okay. So that what happens? This point becomes alpha 1, alpha 2, alpha 3, and this point becomes alpha 1 minus d alpha 1, alpha 2 plus d alpha 2, and alpha 3. So we want the deformed distance now between these 2 points. So you can see one of the changes, differential changes, is negative. Okay. So as a result, this looks like g11 d alpha 1 squared plus g22 d alpha 2 squared minus twice g12 d alpha 1 d alpha 2. This is ds dash 1 2. Okay. So in general, ds I squared is equal to g I d alpha I squared ds dash squared I is equal to g I d alpha I squared, whereas ds squared ij is equal to g I d alpha I squared plus gj d alpha j squared, and ds dash squared ij is equal to g I d alpha I squared gj j squared, minus twice gij d alpha I d alpha j. Okay. So what is now the next step? We know undeformed lengths, we know deformed lengths. Okay. So now it's time to derive expression for strain. Okay. So first we'll do normal strain. Okay. So let's see, epsilon I is ds dash I minus ds I by ds I, which in terms of g becomes square root of g I or small g I minus 1. Okay. So this we write as square root of 1 plus g I minus g I by g I minus 1, and we will assume this to be a very small quantity. in comparison to 1. Okay, that means normally we denote it by a symbol which is epsilon. Okay. So what now we have here is this quantity is epsilon, okay, in comparison to 1, epsilon order quantity. So we have square root of 1 plus capital GII minus GII by GII given by, okay, this is, if this is a small quantity epsilon, then the expansion, binomial expansion, is 1 plus half of that. In order to get it out of the square root, GII minus GII by GII, okay, square root of 1 plus epsilon, the expansion, binomial expansion, is 1 plus epsilon by 2. Okay. So now what is this normal strain? Minus 1. So this thing minus 1. So epsilon II is equal to 1 plus a half GII minus small GII by GII minus a 1. So this cancels with this and I get a half GII minus GII by GII. That is normal strain. Okay. Now what is shear strain? Okay. Shear strain is the given by, okay, shear strain, let's see, shear strain it's like this. We have alpha 1 and let's say alpha 2, and this angle is 90 degrees. Okay, that is 90 degrees or pi by 2. And then when there is a deformation, you get that angle changes. That angle changes. So this angle now, if I call it as theta ij, then epsilon ij is given by pi by 2 minus a theta ij. Okay. So now what is the distance between two such points? What is the distance between two such points? Okay. If we assume this to be a triangle, if we assume this to be a small triangle, what is the distance between these 2 points? That distance is let us say ds dash ij squared is ds dash whole squared ii, this distance, plus ds dash squared jj, okay, this distance. So let's say this is ii, so this, let's say this is this distance, is this distance, this distance, then jj is this distance, okay, then minus, this is just the cosine law for a triangle, no mystery, ds dash ii into ds dash jj into cosine of theta ij. So this you should know from simple geometry. Okay, if I have a triangle and I know the included angle theta, I know this distance and this distance. Okay, then this distance squared is given by this formula. This can be taken as ds dash I, this one as ds dash jj, this is ds dash ij. Okay. Now, but we also know from this formula here, we also know. Okay, so let's rewrite this. So one is ds dash ij squared is equal to ds dash squared I plus ds dash squared jj minus twice ds dash I ds dash jj cos theta ij. Okay, whereas the distance between 2 points alpha 1 alpha 2 plus d alpha 2 alpha 3 and alpha 1 plus d alpha 1 alpha 2 alpha 3, the distance between these two is in our derivation, okay, given by g I d alpha I squared, okay, plus g j j d alpha j squared minus twice g I j d alpha I d alpha j. Okay, so now from here if I bring it down, okay, ds dash ij squared ds dash I, okay, ds dash I we have seen is g I d alpha I squared, and ds dash jj is g jj d alpha j squared. Okay, and this quantity is minus twice square root of g I d alpha I. This quantity is square root of g j j d alpha j into cos theta. So if we equate the two, if we equate these two, this and this, if we equate, this goes away with this goes away with this, 2 goes away, d alpha I d alpha j d alpha I d alpha j, and we are left with, on the left I have g I j, on the right I have root over g I root over g j j cos theta I j. And so cos theta I j, cos of theta I j is given by g I j capital by, oh sorry, my mistake here, this, we are talking dash all the time, okay, we are talking a dash all the time, ds dash, okay, so this will be capital G, This will be capital GJ, my mistake. Okay, so let me correct that here. So this should be capital GII, capital GJJ. So cos theta ij now is this GII GJJ. Okay. Now if we just write down or repeat this expression that we have, Gij, okay, whereas I is not equal to j, is GII del xi I by del alpha j plus GJJ del xi j by del alpha I. Okay. Now this is part of the Taylor expansion on GII. Okay. So this is like a correction term. Whereas Gij involves GII plus summation k del GII by del alpha k xi k into delta ij plus GII del xi I by del alpha j plus GJJ del xi j del alpha I. Okay. So I and j are same over here, so I and j will be same over here, I and j will be same over here. Okay. In that case, what happens? We get GII plus summation k del II by del alpha k. I could have done it just here, xi k. Okay, this is 1 for I equal to j plus twice GII del xi I del alpha I. Now here these are the correction terms, and this is the original first order term. Okay, and these correction terms cannot be bigger than the original term. That's the linear part of the linearity. Okay. So now if I have, whereas in the Gij where I is not equal to j, here I equal to j, I not equal to j, what we have is just the correction term in here, which is a small term. So cos theta ij I am going to write as Gij by, okay, if I have GII plus corrections and GJJ plus corrections, these corrections being small terms, I am going to drop them. Small terms compared to the original order 1 term. So this I am going to write as Gij by square root of GII square root of GJJ. Okay. Then what? Then theta ij, if you remember, theta ij. This is epsilon ij is pi by 2 minus theta ij. Okay. So, theta ij is what? Cos of pi by 2 minus epsilon ij, which is equal to sine epsilon ij, and for small values of epsilon ij, sine epsilon ij is epsilon ij. So, my epsilon ij, the shear strain, is equal to Gij by root of Gii Gjj. Okay. So, I have given an expression for normal strain here, expression for normal strain, and expression for shear strain. Okay. So, we'll now derive actual expression for one of the normal strains. Okay. And we'll do that in the next class. The time is running out here. Thank you.